So my name is Richard Asbury. I'm here today to talk to you about Microsoft Orleans and the actor model and programming the actor model in .NET and what that means. So by way of introduction, I work for a company called 210 Degrees. You can find me on Twitter at Richarama as well. What does 210 Degrees do? Well, we do a couple of things. We run a satellite messaging platform as a service, which basically means we have an API and you can send us a message, we'll route it through to a device on a satellite network, like a sat phone or something like that. And we do the reverse, so if you are a fishing vessel and you fall in the water in the North Sea, you can route a message through to the Coast Guard and the RNLI and they come and pull you out of the water. So we've saved some lives and we've done things like send tweets from the top of mountains and stuff like that. Out of our experiences running this SATCOMS platform in the cloud, we started our own cloud consultancy business as well. So we help other people understand what the cloud is and help software companies move their existing software up to the cloud to make use of the benefits and advantages the cloud offers, as well as architect new software for the cloud. In particular, we work closely with Microsoft and the Windows Azure cloud, and I'm an MVP for Windows Azure, and that's how I got into the Orleans thing. I have the ability to get onto early access programs for technologies that Microsoft want to release or looking at getting some feedback on, and I bumped into the right people at the right time to look at Orleans. So we'll come on to see what Orleans is in a minute, but first of all I want to give you a bit of background into why I think it's an interesting and important technology at this moment in time, and to kind of set the scene where I think we are in our industry is things are starting to change and things are starting to get a bit harder for us programmers. We've had a free lunch for a long time now, and now it's starting to get harder because Moore's law, which says computing power doubles every 18 months or whatever it is no longer being observed by clock speeds getting faster and faster CPUs. It's being observed by things going more parallel, and we're starting to see lots of cores on the motherboard now, and programs having to make the most of those and work in this kind of multi-threaded way. Just as an illustration, you can now get 320 cores on a Windows server, and that looks like that in Task Manager. It's not my machine, but it's a bit of a headache to me. What's interesting when you look at it is that most of these cores, 320 cores, are completely idle at 0%, but that one is at 100%. So there's one process on this box which is not multi-threaded and is not able to split out and take advantage of all these cores, and is being slowed down by the fact that that core can't give it any more power. It's probably Task Manager, but
Office. Happily.
Oh yeah. It's naive to think, of course, that everything can be split into problems that can be distributed across all of these cores, and sometimes things have to be done sequentially, but that kind of illustrates where I think we are. Of course, multi-threading is hard. Who enjoys debugging multi-threaded code when things are going wrong and there's race conditions and there's corrupt state and all those kind of things? These are hard things to navigate through in a debugger and to understand what's going on. So that's difficult, and it's made even harder by cloud computing, which now offers this horizontal scale in hardware as well, so you can quickly burst out to thousands of machines running your software in the cloud. And you thought multi-threading is hard, well, writing distributed systems is even harder. And there's all the problems you get with trying to maintain state across all those machines and having one single version of the truth and things like that. So our job isn't getting any easier. Another interesting note is that because we're looking at running stuff in the cloud these days, we can expect things to fail. The cloud is built out of commodity hardware, and stuff in the cloud fails. When we're running 1,000 machines, we can expect something to break if we're running our system for a short while. This is completely different to how I started software. When I was writing Pascal and basic programs, I was far more concerned about my hardware failing than my crappy software, but now it's completely reversed. You don't care about the hardware, it's just a commodity. So we have to, as programmers, deal with this stuff and deliver software with other demanding customers. And I think some of the traditional in that these approaches haven't been around for that long, but approaches to building kind of 3-tier architecture systems are kind of letting us down, not helping us here. The 3-tier architecture where you consider you've got a database at the bottom and then kind of middleware and then front end at the top. Right. What we do is we take all these concurrency and threading problems and a lot of them kind of move down into the database tier, and that does all the locking and sorts out all of our concurrency worries for us. And that's okay, and the database is very good at handling that and looking at locks and deadlocks in the right way. But it does put a limit on our scalability, so we cannot scale a system that uses a single database infinitely. There will be a point at which this database can no longer handle the amount of data we're trying to get through it. And that's a problem of which there are several solutions, like scale units, where you say, well, I'll just have another system with another database and I'll point customers to the right place. Or you look at some other patterns that can help you around this, or you look at sharding or federation. But these are all kind of just ways of extending the problem. They're not really solving it. Distributed in-memory caches also kind of relieve the database, so you can take stuff out of the data and you can share state without having to go talk to the disk or the database server. But they're really just a sticking plaster. That's just giving you a bit more headroom until you hit the problem in your database again. And CQRS patterns, fantastic pattern. I think there's some talks here today about CQRS. And that's great, that's a good way of getting more scale, and if you don't know anything about this pattern, it's worth having a look at, but it comes with a compromise, and that compromise is eventual consistency, so you no longer have one single version of the truth.
What's CQRS stand for?
Command Query Responsibility Separation. So you would have a write channel and a read channel. So with your Facebook updates, you write all your data to one channel, and then that kind of replicates the data across the world. And so friends in Australia may not see your status update for a few minutes while that thing is being replicated around.
Well, you don't even see your own status.
That's right. And you'll notice that if you do a refresh on Twitter, your tweet might not immediately be in your timeline. It takes a while to appear. That's the kind of CQRS effect. And so you have this eventual consistency world where there's no single version of the truth, and you might get to the truth one day, but there might be a delay. That's fine, and if you can code your application to handle that way of thinking, that's great. But for my world, where I'm trying to pull fishermen out of the sea, that's no good. You need to have a single, very instantaneous view and model of the situation. You can't have two versions of the truth. Okay, so that's me dissing current technology. Let's move on to looking, what is this actor model? Why am I interested in it? Why is this actor model suddenly appeared? Well, it's nothing new. A chap called Carl Hewitt and others wrote a paper back in the 70s explaining what what they envisioned an actor model could be. And they were originally trying to solve artificial intelligence problems, and Carl took a lot of inspiration, not from computer science, but from physics, and looked at quantum physics and a lot of the work that was happening there, and took inspiration for that and built out this way of thinking about software in the same way. I can't personally see how the two worlds combined, but I'm sure Carl's a clever guy. But this wasn't, there were some reference implementations of the actor model, and there were some bits and pieces out there, but it wasn't until Joe Armstrong came along in 1980s with Erlang did the actor model really gain some traction. Erlang has access as a first-class citizen in the language, and since then other languages have come along and popularised it, and there's frameworks like Java's Akka and other systems out there. Of course, Erlang is a nice bit of kit and supports things like CapchDB, React, and RabbitMQ, and of course WhatsApp. So you can build an app and sell it for $19 billion in Erlang. The system works. It's a reliable piece of kit.
I'll sell for $1 billion.
Yeah, 1 billion. So we know the actor model. It seems to be a good idea, and it seems to work in the case of Erlang anyway. But what is an actor? What am I talking about? Let's actually describe what this actor thing is or does. Well, it's a bit like an object really. It doesn't have affinity to a particular thread or process, but it's something that contains logic and behaviour. So it contains code. It is a bit of our program. So that's good. It maintains an internal state, so it has its own internal variables, and you can modify them and change them. They are mutable. And an actor can go and talk to other actors. It can go and send a message over to another actor and say hi, and the other actor can respond back saying, how you doing? What's missing from the list? What can't an actor do?
Persist? No.
Yeah, the platform would have to provide some persistence for the actor. What an actor can't do is modify any shared state. You can't go and modify the property of another actor directly. You can only do that from inside your code. There's no such thing as a kind of shared variable that all these actors can get to. And that's great because now all of our concurrency worries are gone because you're not sharing anything. So what are the other benefits? Well, the main benefit that Erlang gets from the actor model and Erlang's core strength is fault tolerance. Because these actors are all isolated, separate processes, separate bits of sub-process, and have internal state, if one of them fails, it just brings down itself and not the entire system. In an Erlang world, this also allows you to do updates to your software while it's running, because there's no shared memory, you just update the code in the actor and off you go. Concurrency, I just mentioned, there's no shared state, so all the message passing between actors is asynchronous, so you don't have any concurrency worries, no locking required, no locking threading or anything like that. Out of the box, Erlang and other systems support clustering because you have your programming model is asynchronous message passing between small units. That lends itself really well to distributing across that cluster of machines. And Erlang out of the box supports clustering. You can run your software across a number of machines, and your program doesn't really care about where the actors are or any of those problems. And another kind of more subtle but interesting feature of this is you kind of co-locate your data and your logic in the same place. So if you think about a traditional three-tier architecture or something like this, a request comes into a web server, and then that code has to then assemble all the bits of data it needs to then respond to that request, and it pulls that data from maybe a shared cache, maybe from some function over there, maybe from the database. And then when it's finished resolving that request, it maybe throws that away or maybe keeps it in the cache. So you kind of have to move your data to where the thing's being processed. But with the actor model, the approach is that you send the request over to the place where the actor is, which is where the data sits and where the code system is going to process it. So it's a subtle difference. You kind of move your request over in the right place, goes and answers that question rather than having to reassemble the truth every time. So that's all very interesting, but let's get back to this Orleans stuff. What is Orleans? Well, unsurprisingly, it's an implementation of the actor model. So that's good, we like the actor model. It's developed by the Extreme Computing Group, Extreme, in Microsoft Research over in Redmond in Seattle. So there's some really clever brains behind this stuff. And Phil Bernstein, who wrote the book on concurrency in databases, is one of the leads on this. It's a Microsoft internal project, so only for internal consumption within Microsoft at the moment. There is currently a private preview going on, and a very small handful of people outside Microsoft being able to get access to it and are building some interesting stuff. It's designed to run on Windows, and specifically Windows Azure, but can also run on outside of the cloud.
Do you know if they're intending or waiting intending to release it more publicly?
That depends whether I'm being videoed or not.
Sometime in the near future.
Sometime in the near future. There's a conference coming up with 2 slashes at the start. Who won't deal with it. You might want to watch that.
Thank you.
So what are the advantages of using Orleans? Why am I excited about this? Why is Actor Model plus .NET and Microsoft an interesting thing? Well, Orleans is not like Erlang. Erlang, if you want to build stuff with extremely high reliability, go use Erlang. I'm not saying this is a replacement for Erlang. You shouldn't really compare the two things. They use the same actor model, but that's about as far as it goes. Erlang is designed for extremely high fault tolerance. Orleans is designed out of the box to be high scale, low latency. So if your problem looks like a very high scale thing, lots and lots of messages coming into your system, and you want a very low latency, you want to get back to those requests very, very fast by keeping things in memory and not having to go to a disk every time, then Orleans fits that niche. If you want to write a blog post engine, Orleans is not the tool for that. It's not general purpose, it is very specific. It has a very simple programming model. So it's a choice programming, it's really easy. Erlang is not so easy, it's a bit harder. So any .NET developer can approach this without having to learn how to be a distributed systems specialist or have a PhD in that kind of stuff. It's 100% written in .NET and C#, and you can just copy deploy it. It's not like SQL Server where you take a week out to install the thing. It's really simple and easy to get going. What Orleans does is introduces some new terminology for things. So it tries to distance itself a little bit from other actor models, things out there, by inventing some new words. So instead of actors, we talk about grains. I guess it's a more helpful world. It's a really tiny little thing is what you should be thinking about. And we host grains inside a thing called a silo. I guess that kind of makes sense from a farming perspective. That's about as far as the farming analogy goes. So let's have a look at what a grain is. Well, it's a .NET class. Essentially, at the end of the day, that's all it is. And you inherit from a particular interface in your game. When you ask for a grain to be activated for you, so perhaps you want to model your customers, customer X has come into your application, you want the grain for customer X to be instantiated in memory across your cluster of Orleans silos. Orleans guarantees you there'll be a single instance of that grain across the cluster. So you won't have two copies of customer X, you only have one, which is a useful thing to have. So you can go and mutate the state of that customer and you don't have to worry about mutating the state of any other grains. Code you write inside your grain will only ever run in a single thread. So you don't have any thread locking or concurrency problems, you don't have to worry about using the parallel task library or bits like that. You're single threaded. Messages to other grains are queued because your grain is only one of it and it can only run in one thread. If two requests arrive at your grain at the same time, they have to take turns. And so you have a mailbox on your grain and that fills up, and then your grain will process each message in turn and respond back to each one. And grains are completely asynchronous. So we're using async await keywords in C# 4.5, and we should be asynchronous these days. We shouldn't be blocking threads while we're waiting for external systems or things like that. We should be using async code. So what is a silo? Well, a silo hosts grains. It manages the life cycle of the grain. So when you talk to Orleans, you talk to the silo and you say, I want grain X, and it goes and finds grain X. Oh, I haven't got a grain X. I'll create one for you. And it gives you back a handle to the grain. You can then talk to that grain, and that grain stays in memory while you're using it, and so you'll always go back to that grain. So when the grain is first activated, it might want to go and load some state from a database or something to load customer X's records. But once it's in memory, you don't need to go and do that again. It's in memory, keeps it in memory, and that's how you get your low latency and your scalability, because you're not having to go back down to your data tier every time. It's kind of like a cache, but a cache with logic inside it. When your grain receives no further instructions from you for a while, Orleans will perhaps decide that it looks like it's not being used and will mark it for garbage collection. And then the next garbage collection cycle will tear your grain out of memory and you'll be deactivated. You get a notification this is going to happen, so if you want to go and save your state before you die, it's okay. Silos support clustering out of the box, so you can stand up lots of silos on machines, a set of machines, and they'll just work. You don't have to worry about managing the cluster. One clever thing that Orleans does is it can migrate grains while they're running between silos. So if you think about perhaps you're scaling up your infrastructure, you've got all your silos are getting full, you can stand up a new instance. Orleans can then balance out the cluster. So if there's nodes that are hot, it can then move some of the grains over to some of the more empty silos and rebalances out the system for you. So that's quite a clever little feature. It's got quite a smart serializer and can move grains about and you don't have to really worry about which piece of physical hardware you're running on.
So the guarantee of a single instance is across multiple silos?
Yeah.
What is the term for a farm?
Well, I would call it a cluster. Yeah, a farm probably is the best word to use it. Connectivity to the silo to talk to your grain is all done over sockets, and fortunately you don't have to worry about that. There's a nice client library to do all that stuff for you. You don't really care.
Is it similar to Sigma, how they built on Signata?
No. But it's interesting because they kind of sit in the same domain because you've got this low latency thing. And so I have done quite a bit of work with connecting Sigma and all these together. But essentially, well, just come on to looking at a picture of the architecture, which might help clear in your mind how these things will connect together. So what you would do typically is you'd have a worker role in Azure perhaps. So we've got two machines here with Orleans, with the silos running on them like this. You just set them up to be the process that starts in the box. When they start, they go to Windows Azure Table Storage, which is just a key value storage system, and they kind of register themselves there and say, I am part of this cluster, and that's how the cluster management and discovery works. Then what you would typically do is have a web role, so you front all this with your own web application or web API, whatever you want to do. You wouldn't normally allow direct access into all these, although you could do that. When a request comes in to your system, so browser has opened up your web page or something, the client libraries on here go and talk to the storage system and say, well, where is my cluster, what nodes have I got, and then it goes and talks to the right silo in the cluster, and it sends the message to the right grain. That grain will then probably activate itself, and it might need to go and load some information to be able to process your requests. And it can go and talk to a storage system or a database or whatever you need to do whatever your data sits in. And then it can do some work, and perhaps then it goes and talks to another grain, another silo, and needs to tell that something about what it's done. And then eventually you respond back to the web browser. So it's pretty simple architecture. What will probably help though is if I demonstrated what this thing looked like and wrote some code, because I'm not a big fan of doing PowerPoint sometimes. So I've got Orleans installed on my machine. That's not helpful, that doesn't stop the presentation. Hey, okay. I've got Orleans and installed here, just a zip file that I extracted. And it's got the binaries for running the client and the server pieces. It's got some documentation, a little bit of documentation. It's got a local silo, so you can run Orleans locally on your machine. You don't have to run it in the cloud. It's got some PowerShell for deploying these things remotely. There are some samples. And there are some Visual Studio templates, which I've just installed. So let's close up for the time being. Let's go to Visual Studio. We'll do File, New Project. And now I've installed the templates, I've got two new project types that I can choose from. I don't know what this flag is. Anyone knows? It'd be quite interesting to find out. Apparently Orleans is named after New Orleans because after the big natural disaster there, they kind of drew inspiration from putting the chaos back into order, which is what Orleans. So what we're going to do is create something called an Orleans Grain Interface project to start with. So when I said grain is .NET class, I lied. It's an interface in the class. So you have to start with an interface. So we implement iGrain, which is something which comes out of Orleans, and we've got our own iGrain one here. And it's conveniently for us put a little say hello thing on there, which takes a string and returns a string. And because it's asynchronous, are we all C# people here?
JavaScript.
No, JavaScript. My next still one with JavaScript.
But I'm working with you apart from that.
So JavaScript promises?
Yeah.
So the task is a promise,
Yeah.
saying I'm going to get this is going to run asynchronously. I'll get back to you someday and update the result on this object when I'm done. In fact, JavaScript's going to get async away in a few versions time, I think. So have a look at the C# async away and see what you think, because it's quite nice syntax. And
Yeah, we have lots of competing models in NPM, in Node
Yeah.
for handling this stuff.
yeah, and I prefer fallbacks, but so that's great. So we've got an interface there. What we need to do now is actually then implement this interface with a implementation class project, and we'll just add a reference in here between the implementation and the interface, like that. So let's just resolve that. Great. So now we've implemented by grade 1, driving from this grade base class, and we've got our say hello method here, which is returning the string and taking a string and just saying hello. So it's a pretty good hello world. Okay, great. So that's all good. So that's us done. That's all you need to do. But it would be nice to be able to call and activate this grade and see it working. And to do that, I need to write a program to talk to Orleans, because Orleans is just a framework that just hosts this stuff. We need to go and ask Orleans to go and run. So I'll create a console application, and I'll go and add a reference. And what do you think I should add a reference to? The implementation or the interface? The interface, yeah, because the console isn't going to run the implementation, it's going to ask Orleans to run the implementation. It wants just the interface project. And I'm also going to add a reference to the Orleans library as well, which is there. And there's one little bit of boilerplate I need to do, which is I need to go and activate the Orleans client. Who's going to initialize. And the reason I need to do this is I need to tell the client code where the Orleans cluster is, where it's running. And to do that, I've got a bit of XML up here, which I think I can copy into my project. That's easy. And this XML just says, I'm going to be running on port 30,000. So it's straightforward on that address. So that could be on another system, could be in the cloud or whatever. I'll just set that to copy up into this bin folder, and I just want to grab that name, stick it in here. So it knows what's going to initialize. Right, next I want to ask Orleans for a particular grain, for an instance of my grain. And what happened behind the scenes with the interface project here is when I compiled it, some code generation happened behind the scenes. And it went and created a grain 1 factory for us. And that's got a method on it called getGrain. And here is where I say, this is the grain I want to speak to. So we've got two options here, GUID or a long, like a big integer. Anyone got a preference? Anyone know any GUIDs of favourite GUIDs? Go for the number? Anyone got a favourite number?
1.
Number 1, good choice. So we're going to ask a group for number 1 of grain 1. Now we could ask for grain 1000 or 10, and there'll all be different instances activated for us for that number. So we'll get basically a proxy to that grain here, and that at the moment we haven't actually done anything yet. We've just kind of created some client code to go and talk to the grain, but at this point we're actually going to go and talk to Orleans and say hello. We can say hello, more like that. And what we're going to get back, we get task, because this is asynchronous, and then we can do task dot wait, and then we can do console dot write line task dot result, and write our result out, and we've got to fine, otherwise the program will finish me.
That's it. Does that say hello awaitable? Could you have just stuck an await in front of it?
I could have done, but my static main thing
Oh,
here is
yeah.
lacing,
Yeah.
and I don't think it will run if I do that. But yeah, in fact, you don't need that line, because weirdly, the result will block until the task is finished, which I think is bad. But there you go.
You wrote something about that recently, didn't you?
Yeah, I did write that. I
I
wrote a rant, yeah. Why? It's good practice to not block in properties, anyway. One last thing we need to go and do is we need to go and move our DLL we've written here, our implementation of the grain, over to the Orleans folder, so it's got a copy of it, because it needs to have our code to run our grain. That kind of makes sense. So we're going to put it in a local silo. So we just set, so when it builds, it goes and copies the DLLs there. So let's build the solution. Compile, that's surprising. Have I done anything? I think so. So let's go into Orleans, and there's a script on there called start local silo. What's that whole load of stuff? I have no idea what that means, but it looks really cool. And in a minute it'll say ready.
What's this window you're running here?
This is just a prompt, but I'm using command, which is quite a nice little prompt thing.
Okay.
So this needs to be online at the moment, and I'm suspecting that I'm not online. No, let's see if this thing works. No, it doesn't look like it, does it? Oh, no. Let's try this again. Good. So let's just stop that. And,
Why does this need to be online?
it doesn't need to be for now, but it will do for my next one. And now I've got Orleans running. It's automatically picked up the DLL. It found it in the right folder and knows what to do with it. So I can just press. I need to set my console applications to startup project. Press F5. Hello Norwich. There we go. So it works. Quite surprising. So, hopefully, it's a very simple naive demo, but I hope that kind of illustrates it's not that hard to get this stuff running. There's not too much weirdness and going on. So let's close this. I want to show you a slightly more interesting demo, which does a few more bits. And what we'll do is we'll stop that. We'll rebuild this, just to make sure the DLL gets in the right place. And I'll run it, and then that'll make it easier to see what it kind of does. Go on, membership Oracle. You can do it. I'll just start my application, which is actually part of it is Node, we used to see. And what this does is it pulls in the Twitter streaming API. So it's putting in just a sample of all the tweets that are happening around the world. I apologise in advance if there's any offensive language in there. And what it's doing is for every tweet that's coming in, it's running a sentiment analysis on it to try and see whether it says something positive or something negative or indifferent. And then it looks at all the hashtags in that tweet and then records the score against each hashtag. So it's quite a neat little way of building up an idea of people's thoughts on a particular subject, for example, Norfolk Developer Conferences, and getting a kind of global view of what people think. So here's a web app which then talks to Orleans and pulls out the grains for some of these hashtags. And unfortunately there's not picked up anything from NorDevCon.
At least twice this morning, too.
Well, this is only a sample of the 5 there, so LOL is generally positive, so it shows you the system generally. I don't know what MTV stars is, probably something to do with MTV, but there's always someone using that in a hashtag somewhere in the world. So, quite a simple app, but So what we've done here is we've modelled each hashtag as a grain. So you go and tell hashtag grain lol that there's a new positive thing about it, and it'll go and update the score. It's just refresh. So you should be seeing that these numbers change as we go. So great, that works. Let's have a look at quickly how this thing is put together, because there's a few more features and all-ins that it has to be used to work. So we have at the heart of it this hashtag grain, which this is the interface for it. It's quite simple. You just add a score, so positive, negative, or 0, and it has a method on it to get the score for that grain. So it maintains an internal state in the grain, which is the current score. Now, spot the problem that we had earlier, because we have, when we wanted to ask for a grain, we had two choices, didn't we? We had GUID or long. Now, hashtag is neither a GUID nor a long, so we could use those things, but you'd have to do some nasty lookup or something. So we've got this attribute we can add on called extended primary key, and that allows us to have a secondary key, which is a string. So we can use that secondary key as a way of identifying this grain. So that allows us to augment the key and use the hashtag. Now if we actually have a look at hashtag grain, it doesn't do anything much exciting, but one thing you may have noticed when we started the app is that these things didn't start on 0. They had a score they had already. So where did that come from? Because all the ends was completely stopped and then starting again in between the demo. So it's because the grain has a state and it's persisting that state when it's being deactivated. The way that works in all-ins is you can go and do that yourself, or you can say to all-ins, look, I've got this state here, I've got some totals I want to store. Those totals look a bit like this. I've got a number of positive, number of negative, and a total number of tweets. And I want to go and use this place to store that stuff. So when all-ins activates your grain, it goes and talks to that store, pulls out the state for your grain instance, and then sets that on a member property of your grain called state. So then I can modify this state thing, and then when something happens in my grain that means that I want to preserve that state, for me, if there's a non-zero score, so it's either a positive or negative tweet, that's interesting for me, so I want to go and save that, and it stores it for you. You can see the await word being used there, which is the nice bit of semantic sugar for async in C#. And then, of course, for get totals just then returns the state, essentially wraps that up in a different object. But as an optimization, I don't want my client code to go and activate all the hashtags, all the grains for each hashtag in the tweets, because a tweet could contain lots of hashtags, so it's inefficient to go and, in my client code, talk to all-ins for each one of those. So I'd rather just pump in a message to saying, this is a score for these 5 hashtags, go and update those all in one go. So it's a bit more efficient for me. And to do that, I have a tweet grain, which just has a score and the hashtags that have that score. So I can push all those hashtags in at once. So when I said you can only have one instance of a grain in the whole cycler cluster, that was also a lie. Because you can have a stateless worker. So this grain has no state. It doesn't hold anything. It just acts as a conduit to pass on the message to all the grains for those hashtags. So it's okay to have more than one of those. So all-ins will make sure there's one of those in each silo, so there's always a local one available for your grains to consume. And it'll auto-scale it out. So if there's the mailbox on that grain gets to a certain size, it says, right, let's spawn another one. And it goes and auto-scales that, pairs that back when you need to. So it's quite a nice little feature. How then do we talk to how does one grain talk to another grain? Well, it uses exactly the same technique as our client code did. You use that factory. This stateless worker goes through all the hashtags and then activates the grain for that hashtag, which may or may not exist. It doesn't care, whatever it does, it goes and then adds the score for that grain. Now, what's the worst possible thing you could do with async code here would be to await every single add score, and then you serialized out this thing. So one thing happens after the other, and you wait for the last thing to happen. What you want to do is fire up all of those things at once and get all the answers back in one go. How do you do that? You collect up all the promises, all the tasks, and then await the lot, which is not particularly obvious to me, but that's how you do it. That's an async fan out. So just because you're running a single thread doesn't mean you can't do more than one thing at the same time. You just have to think in this asynchronous way of doing it. Any questions on that before I...
What's the zero in the get grain?
When you have extended primary key, because I wanted to have a string as my key for the grain, you still have either the long or the GUID.
Right.
So I don't really need to use that, so I just set them all to 0. It's because it was a bit of a hack that was put on after I gave them some feedback. So that's interesting. So I think that kind of demonstrates a little bit about how grain can be used and how it modifies its state and how the storage works and how status workers work. There's a lot of concepts here, and I'm not going to quiz you at the end, but I just want to give you a flavour of some of the things this can do. So let's zip down here and resume where we left off. So let's check the time, we've got a couple of minutes left. Yes, so what are the use cases of Orleans? Why am I excited about it? What do I think we can use it for? Well, Internet of Things is one kind of obvious thing that's coming up. We know we're going to have lots of devices on the internet. They're all going to be reporting back with some kind of telemetry. It would be useful if you could write some simple server-side logic so that you could say, if my fridge is empty, then go and order some more baked beans or whatever. So being able to compose grains which model these devices is quite a compelling use case, I think. Low latency, high scale, real time kind of situations are often required with these Internet of Things. We do work with small devices stuck on things like oil rigs, where you want to build up a model of the oil rig. Is the thing going to explode because the pressure in the pipe's got to this and the pressure over there is that? And being able to do that in this kind of system is pretty good. But the biggest user so far of Orleans, anyone know?
Halo?
Yeah, Master Chief is Williams was never written for Halo, but it was a kind of happy coincidence. The Halo team were looking for something that looked like Orleans, and Orleans were looking for someone to use it. And so all of the server-side processing in the Halo game is all done through Orleans. And there's a lot of server-side stuff going on with Halo. Every single thing you do in the game is reported back to the cloud, and that enables the second screen that you can get with Halo and all the website and all the stats. And the reason they chose Orleans was basically this graph, which shows the throughput of the system on the y-axis and the number of servers in the cluster along here. And the interesting thing is, it's a fairly linear line, which is surprising for a large distributed system. I should say it's a good sign. And this isn't just a naive hello world, this is an application that uses at least 2 grains. One grain talks to another grain. They're probably not on the same machine, so there's cross-cluster communication in this load test. And this is the actual kind of Halo 4 system. So what now? What next? What are we going to do? Well, watch this space. We mentioned that there may well be an announcement coming along at a nearby big conference. So keep your eyes open for that. Follow me on Twitter. I'll be tweeting, blogging about it, and hopefully supporting the launch of Orleans when that comes out. So we're kind of out of time. I don't want to eat into your presentation, but any quick questions? You can always come from the bottom of the office.
Yeah, just like obviously this isn't released yet. In terms of the program looks really simple, but in terms of the way of thinking about how you design and build a program, is there any kind of like background reading kind of heads up stuff that would be worth looking at? Does it change the way you design a bit of software quite dramatically?
It
Even
does.
as a simple model.
Yeah, you do have to think carefully about how you model stuff with grains. So, for example, what you don't want to do is funnel all of your bandwidth into like a single grain, because that's taking this whole distributed architecture and then pipelining all through one then single point of failure and single piece of kit. So building your software in such a way that you don't have those problems in your software is the biggest headache, I think, in designing all these systems.
Was there any kind of background reading or stuff you found useful to get to that point you could do that? Was it just trial and error?
Getting familiar with async await is probably a good place to start, and programming in .NET 4.5, having a knowledge of Azure is probably a good place to start as well. I can't recommend any books. I'm thinking of writing one, but I'm not quite there yet.
Are there any similar technologies like implementations of the actor model in open source or any other?
Yeah, Akka is the place to look at, which is a Java implementation of the
Cool.
Akka. I think it's AKKA or ACCA. I'm not quite sure. I've not looked at it, but that's probably one place to look. The other is obviously Erlang.
What was, you talked earlier about fault tolerance with Erlang. In terms of, or Linux, what's the fault tolerance like? So say that the cloud system holding one of your silos falls over, well, before it's written its state or something. Is there any tolerance?
There are tolerances, so it will the cluster will understand when a node drops.
Okay.
The cluster monitors the time a gradient takes to respond, so if your gradient takes more than 30 seconds, it kills it.
Right.
So you shouldn't be doing very long
Stuff.
I can't think of anything else. If failure will happen, you will still lose data. If the machine's switched off, then everything that was unsaved will be unsaved. But if you save stuff as you go,
So it's thinking about it in very small chunks.
Yeah.
It's a different way of thinking.
that's right.
I noticed in your example,
Last question.
you asynchronously wrote the state of the grade to the persistence layer each time it was updated.
I did. Actually, I only did it when the score was interesting.
Okay,
From 0,
that's true.
But you were right. You kind of negate
Could you
the
just
whole
wait
point of it.
until the grain was killed and write a kind of cleanup?
You absolutely could, yeah, and that'd be a better way of doing it. But the grain, if the silo was destroyed, you're going to have to decide how important this information is. Thank you very much.